When life terminates for a star, it collapses inward and forms a black hole. Is the surrounding region of space affected? What is the definition of space-time curvature in terms of gravity?
One may imagine space-time as made of sort of a rubber membrane onto which you put a sphere made of steel, which deforms this rubber membrane. This observation comes from the fact that nature seems to be lazy. That's a principle which has been formulated in the French mathematics of the French Revolution and was first formulated by d'Alembert. It's d'Alembert's principle, or the principle of minimal action. That means that objects, but also light, move along lines of minimum action. Action is a product of energy or force times space. So the lines of minimum motion in gravitation is defined by matter and additionally by energy, according to Einstein's famous relation E equals to m times c squared. How can one prove that? The first observation of the validity of the general theory of relativity was the observation of the movement of the perihelion of the orbit of Mercury, made during a solstice in 1919. Another good example are gravitational lenses. Gravitational lenses consist of a huge amount of dark matter, which is in between of us as observers and very luminous objects like quasars in remote region of space. And such remote objects are depicted 2, 3 or 4 times by gravitational lenses, so they are multiplied in observation. This hints to a very strong deformation of the space-time curvature. Another example is the global positioning system, where the clocks in the satellites are running much faster than the clocks on Earth. And we have to correct for this difference in our global positioning systems. This tiny difference between the clocks running in satellites and on Earth is due to the different gravitational force up in the satellite and down to Earth.
Broadcast system. Electronic music.
What is the true nature of gravitational waveforms? Are they longitudinal or transversal in behavior? Can they be detected? Can single pulsations affect the fabric of the space-time continuum?
You can imagine gravitational waves as a sort of wiggles or ripples of space-time, and they are so-called tensor forces. A tensor is a mathematical object which mediates between a vector and a vector. So the question of transversity and longitudinality is not is an experimental issue which has to be clarified still. An important observation has been done in starting from 1973 and 4 by Hülse and Taylor who observed that a binary pulsar system slowed down its rotations due to the apparent loss of energy in gravitational waves. This spectacular discovery was honored by the Nobel Prize of 1993. Gravitational waves would distort or shorten the distance to the nearest star by less than the thickness of a human hair, or if you take apparatuses on Earth of the order of kilometers, by less than 1/1000th of the diameter of a proton as a nuclear particle. Such interference spectrometers have been built, for example, the GEO 600 device near the German city of Hanover, which just started operation and aims for observing gravitational waves. A much more sensitive device works in the United States, the LIGO Observatory, which consists of 2 arms of interferometers of a length of 4 kilometers. And it has also been planned as a common project of the European Space Agency and American NASA to launch several satellites starting from 2013, which will circulate around the Earth at differences of several million kilometers and probe the oscillating nature of space and time. LIGO and LISA will be able to measure the effects of coalescing or spinning black holes and neutron stars, or even to be sensitive to the so-called primordial gravitational waves, which are the remaining whispers of the Big Bang.